The mean value theorem is probably one of the most useful results in analysis. Let's say you have an interval I, and f is a function from I to R. We'll say that the function has a relative maximum C in the interval if you can find some delta positive such that function at x is going to be smaller than the function at C, or all of the x's in the neighborhood of radius delta around C. So graphically, what we're talking about here, the point C and some neighborhood around the point C of radius delta, so the length here is delta, such that if you were to take the value of the function at any point in the interval, it's always going to fall below the value of the function here. So the function has a relative maximum at the point C if you can find a neighborhood satisfying this condition. And of course, you also have the idea of a relative minimum at some other point. Let's say, I don't know, let's call it E. If there's some neighborhood with a different radius where the value of the function at all the points in the neighborhood will be above the value of the function at the point E. I am not writing out the definition here. Are you able to write the definition for the relative minimum? This isn't quite yet the mean value theorem, but it's a result that's going to be useful for us to prove the mean value theorem. In my version of the notes, this is Theorem 43. So you have a function f from some interval ab into the reals, and c is some point in the interior of the interval ab. If f has a relative extremum at c, so either a relative maximum or a relative minimum, and if f is differentiable at c, then the derivative at the relative extremum is 0. Now, I alluded to this when I drew these horizontal lines here. From calculus, we know that the derivative represents the slope of the tangent line. And we know that when we try to optimize a function, we're looking for points where the slope is 0. When we talk about the Max-Min theorem, you'll discuss this from an analytical perspective rather than a calculus perspective. So we know what the assumptions are. We have a function with a relative extremum at C, which is differentiable at C, and we want to show that the derivative at C is equal to 0. I'm going to do the proof here, assuming that the relative extremum is in fact a relative maximum, but it would be a good idea for you to see if you can recreate the proof if you assume that instead the function f has a relative minimum. Without loss of generality, let's assume that f has a relative max at c. We want to show that the derivative is equal to 0. We're first going to assume that it is positive and see that this leads to a contradiction. Then we'll assume that it's negative and see that this also leads to a contradiction, and then we will have no other choice. If it can't be positive and it can't be negative, it has to be equal to 0. If the derivative at c is positive, then you can find a delta, also positive, which will guarantee that the differential quotient f at x minus f at c divided by x minus c is greater than 0 whenever x is in a neighborhood of c, of radius delta, assuming of course that x is not equal to c. Well, how do we know this? We know the definition of the derivative, right? For every epsilon greater than 0, you can find a delta greater than 0 such that the absolute value of the difference between the differential quotient and the derivative at the point C should be smaller than epsilon whenever x is in a neighborhood of radius delta around C, excluding the point C itself. Now, if this is true for every epsilon, in particular, it is going to be true if epsilon is equal to 1/2 of the derivative of the function f at c. I can say this because f prime at c is assumed to be positive. So 1/2 of f prime at c is positive. That is one of the multitudes of epsilon that you could have, which is greater than 0. So there's going to be some delta, which will guarantee f at x minus f at c divided by x minus c minus f prime at c in absolute value will actually be smaller than epsilon, which we said here was 1/2 of the derivative whenever x is in a neighborhood of radius delta centered at c, excluding the point c itself. Now let me use the definition of the absolute value here. What this means that f at x minus f at c divided by x minus c minus f prime at c is sandwiched between minus 1/2 of the derivative and 1/2 of the derivative. So now, if I concentrate only on this part of the inequality, I'm going to send f prime at c to the other side of the inequality here. We'll get that the differential quotient fx minus fc divided by x minus c is greater than 1/2 of f prime at c, which by assumption was positive. So I found a delta, the delta that worked here, which guarantees that whenever x minus c in absolute value is smaller than delta, f at x minus f at c divided by x minus c is greater than 0. But that's not good. Why isn't it good? Well, now if you pick x in the neighborhood of radius delta around c, which is to say, if this relationship holds, and if you're on the right of the point c, so here's your c, here's your delta, you're picking an x somewhere in here, you will have that f at x minus f at c that is going to be the same thing as x minus c times f at x minus f at c divided by x minus c. But I'm just multiplying by 1 in a very special way. For every one of these x's in there, this quantity is positive and this quantity is positive. So f at x minus f at c is positive, which means that f at x is greater than f at c. But that's impossible. It's impossible because we had assumed, previous slide, that f had a relative maximum at c. And here what we found is that for any point in the neighborhood greater than c, f at x would be greater than f at c. So in particular, f cannot have a relative maximum at c. It's impossible. So the conclusion here is that f prime at c cannot be positive. In a similar way, you can show that f prime at c cannot be negative. You don't have a choice. The only possibility is that the derivative at that point is equal to 0. Of course, this argument only works if the function is differentiable at c. It is possible that the function would have a relative maximum at a point c without the derivative being equal to 0, because the function is not differentiable at the point c. This result here justifies the common practice of looking for relative extrema by looking for points where the derivative of the function is equal to 0. An important note to make is that the point c has to be in the interior of the interval ab. It's not one of the endpoints. So whenever you do look for relative extrema of a function, it is not enough to find these points where the derivative is equal to 0, assuming the function was differentiable. These critical points, you also want to find the points where the derivative might not exist and include the endpoints of the interval. Now, it's not sufficient to find points where the derivative does not exist. We can come up with a function where the derivative exists nowhere. So you are specifically interested in points where the derivative does not exist only if there's a finite number of them in an interval. Right? If you look at the function from the interval minus 1, 1 to r, defined by the absolute value of the function. There's a critical point, there's a relative minimum at the origin, but because the function is not differentiable at that specific point, at that relative minimum, we can't apply the theorem to conclude that the derivative of the function would be 0. Our next theorem is a named theorem, one of the important ones. Theorem due to Rolle. I guess in English you would call him Rolle. Rolle's theorem, the Theorem de Rolle. Let f be a continuous function on the interval AB into the reals. Assume that it's differentiable on the interior of the interval AB, so the open interval AB. If the function takes on the value 0 at both A and B, then you're able to find some point in the interval such that the derivative at that point is 0. Does this make sense? Let's draw a little diagram here. Say this is A, say this is B. At A and B, the function takes on the value 0, and it's continuous. There's got to be at least a point where the derivative of the function is 0, assuming the function is differentiable on the open interval AB, and here we actually have 3 such points. Alright, this is at least a sensible theorem. It makes sense. This is at least a sensible theorem. It does make sense. Now, how do we prove this? Well, if the function is identically 0, then every point in the interior has a derivative which is equal to 0, right? Because the derivative of a constant function is the 0 function. So that's good. So now we're going to assume that the function is not identically 0. Then there exists some point, which I'm going to call x star, where f at x star is different from 0. So this could be a point here, and the value of the function f at x star is not equal to 0. There's going to have to be more than one such point if the function is continuous and it's not equal to 0. But there's at least one. Without loss of generality, let's assume that the value of the function there is actually positive rather than negative. The proof works just as well if f at x star is negative, but there'll be a few things you need to modify along the way. So we are assuming that the value of the function at that point x star is positive. By the Maxmin theorem in chapter 4, f will reach its supremum somewhere on the interval AB. That's because the function f is continuous and the interval AB is compact. But we know that fb and fa are both equal to 0. So the somewhere in question is actually in the open interval. And we know it has to be somewhere other than at A and B because there is some point on the interval AB which is positive, and that point is not the endpoint A and B. So the function cannot reach its supremum, its maximum in this case, at either of the endpoints of the interval. Let's say that that point where it reaches its maximum is C. So now you have a function which is continuous, it is differentiable, it reaches a maximum, which is a global maximum here at the point C, but a global maximum is also a relative maximum in its neighborhood. And by the theorem that we've just seen, theorem 43, the derivative of the function must be equal to 0 at that point. That concludes the proof. Let's go over this one again, just to be safe. If the function was identically 0, the derivative was identically 0 as well, and we've proven the theorem. If the function was not identically 0, there is some point in the interval which cannot be the point A or the point B where the function is not equal to 0. It can't be A and B because by assumption the function is 0 at A and B. Whether the function is positive at that point or negative at that point is irrelevant. The same proof will work, but as soon as you know that one of the values of the function is not equal to 0, then the max-min theorem kicks in. Because you have a continuous function on a compact set, you know that the function reaches its supremum somewhere in the interval. And the supremum has to be greater than 0 because of this assumption here. Or at the very least, it has to be different from 0. You're going to be using the min part of that. It could be reaching its minimum at some value which is not equal to 0. It reaches its maximum somewhere on the interval, but it cannot be at the endpoint, so it has to be somewhere in the interior, in the open interval AB. Call that point C. And now we have all of the conditions for theorem 43 to apply. Automatically, we know that that point has to be a point where the derivative of the function is equal to 0.